Hello and welcome. I wanted to create a video where I go through an example problem of using planar kinetics for a rigid body. This is chapter 16 in the Planar Dynamics text, and basically what we've done is we have gotten rid of our particle assumption. So we are now dealing with both moments and some of the forces to find the unknowns in any problem. So we're going to have equations of motion for both moments and forces. And here's the problem that we're going to work on. 17-103, this is from the Planar Dynamics text on page 449. If the truck accelerates at a constant rate of 6 meters per second squared starting from rest, determine the initial angular acceleration of the 20 kilogram ladder. Ladder can be considered as a uniform slender rod. The support at B is smooth. So I'm going to start writing down my givens here. So the truck accelerates at a constant rate of 6 meters per second squared. So I'm going to write a section for givens. And say that the acceleration of the truck is equal to 6 meters per second squared. Starting from rest, so that tells me V naught equals 0. Determine the initial angular acceleration of the 20 kilogram ladder. I'm just going to put the mass of the ladder down. The ladder can be considered a uniform slender rod. That gives us a big hint right there. Because we're going to be dealing with the moment of inertia of this ladder, we're going to have to go to the back cover of the textbook to find the moment of inertia of a slender rod. The ladder can be considered as a uniform slender rod. The support at B is smooth. That's just telling us that B is going to be a normal force. And we're supposed to find the initial angular acceleration of the ladder. And I'll just mark that as alpha because it's the only angular acceleration we're going to have. To get started on this problem, we have to take a careful look at it and see the different options on what can happen. And a lot of the problems that involve friction will be very similar to this one, where there might be more than one thing that can happen. In this particular one, if this truck is going at 6 meters per second squared, ask yourself, what could this ladder do? Well, it looks like there's no support at B. It looks like it's hitting the tailgate at A. So we won't be seeing it sliding at A. Even if you didn't know there's a tailgate there, you still have a really good hint that you're not going to be dealing with any sliding at A. And that hint is that you know absolutely nothing about the friction at A. There's no kinetic friction given, there's no static friction given. Without any of that information, we couldn't do sliding at A. So at A, we're going to assume that that's being held by the tailgate and that there could be a moment applied there, but both the X and Y directions is going to be fixed. So if this truck is accelerating, there's a couple things that could happen. If the truck's not accelerating fast enough, the ladder's just going to stay there. If it's accelerating fast enough, the ladder is going to rotate at point A and fall out of the back of the truck. So the very first thing we want to do is figure out, is this ladder going to rotate at all? Maybe the answer is 0. Alpha could be 0. And to figure that out, we can set this problem up and draw a free body diagram and figure out at what acceleration will the ladder start to rotate. And that's how we're going to start the problem out. So to start off with that, the very first thing I'm going to do is draw a free body diagram. Now we have a truck and a ladder, but we're really just dealing with the ladder. The truck is just there to provide acceleration. So I'm just going to draw the free body diagram of the ladder. I'm going to label it because we're going to have a kinetic diagram as well, and I want you to be able to see the difference. So my free body diagram, I'm going to have the ladder. And if we look at B, we know there's going to be a force at B. It's going to be perpendicular to where B hits the ladder. I'll call that N sub B, or the normal force at B. Other places where this ladder touches something, well, at A, it's touching something. The floor of the truck bed is holding it in the Y direction. So I'll call that AY. And then the tailgate is holding it in the X direction. I'll call that AX. So we have what's equivalent to a pin support at A. One more force that's going to be acting on this is, of course, the weight of the ladder. And that's going to occur at the center of gravity of the ladder. Now if you notice, when you're looking at the drawing, this is 2.5 meters, that's 1.5 meters, so center of mass should be slightly below B. So I'm going to draw it somewhere down here and call that W. Okay, so we've got the weight, the normal force, and then we've got the reaction forces at A, and that does it for our free body diagram. We also are going to need to use some angles, so I'll just go ahead and put in an angle, the one that's given here of 60 degrees. So we're given 60 degrees. Okay, that's my free body diagram, and that's going to be very useful in figuring out this problem. But it's not the only diagram I want to use. I also want to use my kinetic diagram. In your kinetic diagram, what we're going to do is we're going to actually draw the motion of the center of mass, and we're going to draw the point A because we know where A is going as well. So I'm going to redraw that ladder just next to it over here. And remember, in the kinetic diagram, we're not drawing forces, we're drawing pseudo-forces, and those pseudo-forces come out of the acceleration of the center of mass. This first portion of the problem that we're solving, we're assuming that nothing's happening. Okay? We're assuming for a critical point. That critical point would be where the truck is accelerating just enough so the ladder does not rotate. If we can figure out what that acceleration is, if it's less than 6, then we know our ladder is rotating. If it's greater than 6, then our ladder is just staying still. So this is a good first step to see what's actually happening to the ladder. So with this critical point, we're going to assume the ladder's not rotating. If we assume the ladder's not rotating, where's the center of mass going? Well, it's going right along with the truck. It would be going in this direction. Be the acceleration of the ladder in the x direction, and we of course multiply it by the mass. There's my kinetic diagram with the acceleration of the center of mass of the ladder in the x direction. I'm also going to go ahead and put my angle on there like I did on the last one. Obviously it's the same angle, 60 degrees, and then I'm going to put a distance on this one of 2 meters because we know that the center of mass is going to be right in the middle of that rod. Total length of the rod is of course 4 meters, the 1.5 plus the 2.5, and halfway up is going to be that center of mass. So there's my kinetic diagram. And I'm going to put my point A down here. And the important part is that we want to find the critical point where it's just about to rotate but it's not rotating. You have to ask yourself, what would that critical point be? The critical point would be when this normal force at B here, would be equal to 0. That means the truck's accelerating just enough so that there's no force on B, and we can use that as our critical point. So if that's 0, then we can come up with our sum of the forces in the x and y direction, and we could come up with our sum of the moments about A. And we could do that a couple different ways. We could do sum of the forces x, sum of the forces y, and figure it out from there, or we could use our kinetic diagram. If we use our kinetic diagram, the equation that we use is that the sum of the moments about a given point, and in this case it's A, are going to be equal to the kinetic moments, the sum of the kinetic moments. The book just uses a funny looking M. The kinetic moments at point A. Well, what do the kinetic moments mean? The kinetic moments is where you use that pseudo force and multiply it by distance to figure out the moment that would be, or the kinetic moment that would be caused. So let's look on the left hand side and find the sum of the moments about A. When I say left hand side, I'm talking about the free body diagram. We're going to use the free body diagram for this side, and we're going to use the kinetic diagram. I'll use a different color here. Kinetic diagram for the right hand side. So starting off with the free body diagram, we're doing the sum of the moments about A, and we also have to remember that we're setting our critical point. So I'm just going to erase this NB and write it out very specifically that at this critical point our normal force is equal to 0. If our normal force is equal to 0 and we're finding the moment about A, there's only one force that would cause a moment about A, and that would be the weight of the ladder pushing down on the center of mass. We know that it's 2 meters to that center of mass, and we know that there's 60 degrees. So what we need to find is we need to find the distance from here to A, this distance right here. And that's fairly simple because we know we have a distance here of 2 meters and we have an angle of 60 degrees. So it would be 2 meters times the cosine of 60 degrees. So I'm going to go ahead and write at that moment out. One check we have to do is also figure out if it's positive or negative. To do that, I would put my thumb on A, I'd point my fingers towards the weight force, and it would tend to curl my fingers, which means it's positive. So the positive moment would be weight times the distance, which we already said was 2 meters, times the cosine of 60 degrees. Okay, so the weight times 2 meters and cosine 60 degrees, that's the sum of our moments about A from our free body diagram. And now we're going to set that equal to the sum of our kinetic moments from the kinetic diagram. Now, we're looking at something very similar here in the kinetic diagram, but we're looking at that pseudo-force. That pseudo-force is the mass times the acceleration of the ladder in the x direction. Luckily, we already know what that would be if it's not rotating, because it's going to be the same as the acceleration of the truck. So that's why this is a nice shortcut to just check before you actually do all the calculations and see, is the ladder really rotating? So what we're going to do now is we have to figure out the distance from the line of action of this pseudo-force to A, which would be this distance right here. Now, of course, that distance is the same as this distance, which hopefully you can see right away is just going to be 2 meters times the sine of 60 degrees. So that is equal to our mass times our acceleration of the center of mass of the ladder in the x direction. That's the pseudo-force, and the distance is 2 meters times the sine of 60 degrees. Okay, we have enough information here now to solve for that acceleration that would cause the ladder to rotate. So the weight of the ladder is 20 kilograms. I'm going to go ahead and plug that in. I'm sorry, that's the mass of the ladder. So we have to find the weight of the ladder. I'm going to put it up here in my givens. The weight of the ladder is going to be equal to 20 kilograms times 9.81 meters per second squared. Now I can put that into my equation. I have 20 kilograms times 9.81 meters per second squared. We see that kilogram meter per second squared gives us newtons, and we're multiplying that by 2 meters. That's going to give us newton meters, which is good because we're dealing with moments. Times the cosine of 60 degrees is equal to our mass, which is 20 kilograms, times the minimum acceleration of the center of mass in the x direction. That would cause this to rotate. That's what we're solving for. Times 2 meters times the sine of 60 degrees. Okay, at this point we just have to solve for the acceleration. Acceleration in the x direction is going to be equal to 20 kilograms. Luckily we have another 20 kilograms. It's going to cancel that out. And then we're going to, and we multiply that by 2 meters, which is also going to cancel out. We have 2 meters on both sides. Both of those cancel out. And then on top we have 9.81 meters per second squared cosine of 60 over the top of sine of 60. Quick calculation will give us the answer to that one. And we get that the minimum acceleration of the center of mass of that ladder in the x direction to cause rotation is 5.66 meters per second squared. Now we look at the problem and we say 6 meters per second squared is the acceleration of the truck, which means the ladder is rotating. So this was a nice easy check to figure out if it's rotating or not. Now we're going to move on and solve the problem knowing that the ladder is rotating. So now we're going to switch over to solve the problem of the initial angular acceleration of the ladder. And to do that, I'm going to go back and draw the same two diagrams, the free body diagram and the kinetic diagram. Free body diagram really doesn't change because we know that the ladder is going to be rotating. If the ladder is rotating, then there's no force at B because it has lifted off of B and it's moving. So I'm going to go ahead and draw that same free body diagram we had before. We've got our AX, our AY. We've got our weight right in the middle, pushing downward And I'm not going to draw the normal force of B because we know that it's rotating, which means it has already lifted off from B. So those are the forces that we have, and this is going to be a distance and an angle. Let's put those on here too. There's 60 degrees, and we've got our 2 meters to the center of gravity, G, which is where the weight is acting. For a kinetic diagram, we're going to have something a little different because now we know it's rotating. So our kinetic diagram is going to have acceleration of the center of mass in both the x and y direction because it's going to be rotating, it's going to be pivoting on A. So let's go ahead and draw that. I'm going to draw that center of mass here. And we know that there's going to be some acceleration in the x direction. We'll call that AGX. And there's going to be some in the y direction, AGY. Now, of course, those are not pseudo forces, those are just accelerations. So I'm going to add an m to each one of them. So now we have MA, which is a pseudo force. I'm going to put my point A down here. And there we go. And I also have to draw in the pseudo couple moment, which is due to the acceleration alpha. And that's always going to be about, if you're doing the kinetic diagram like we're doing here, it's always going to be about the center of mass. It's going to be equal to IG alpha, where that alpha is the same alpha as what we're solving for. It's only one alpha for every rigid body. So we got our couple moment IG alpha, we've got our 2 pseudo forces, and we've got our point A. I'm going to go ahead and add in our 60 degrees angle and our 2 meter distance. Okay, so we got everything we need there in our kinetic diagram. We could even do a little bit more. I wouldn't want to draw it on the same diagram because we don't want to mix pseudo forces with accelerations or velocities, but we know what A is doing. We know that A, I'm just going to draw it separately here. The velocity of A is going to be equal to the velocity of the truck, right? Because we have that AX and that AY holding A right in the truck bed. So that's nice. We know that the velocity of that one point is going to be equal to the velocity of t. What do we know about the acceleration of it? Well, we know it's going to be exactly the same, right? The acceleration of point A is going to be equal to the acceleration of the truck as well, because it's just going to be pivoting about A. And if the truck is accelerating, A is going to be accelerating as well. We know that's going to be in the negative x direction. If we have our coordinate system, kind of made an assumption here that our coordinate system is the general xy. It's always a good idea to expressively state that, because you could do normal tangential in this problem. Okay, so with that, now we have to figure out the same equations we had before. And the equation we had before was that the sum of the moments about a point, and obviously we're going to use A in this case, can be equal to the sum of the kinetic moments, that's that funny looking M again, about A. The sum of the moments about A, well, the sum of the moments about A is fairly easy. That's the left-hand side, which we're going to get from the free body diagram. And we have our weight pushing down. We have the 2 meters times the 2 times the cosine of 60. I'm going to go ahead and write that out directly from the free body diagram. We've got the weight pushing down, which is our 20 kilogram times 9.81 meters per second squared times the 2 meters times the cosine of 60 degrees. Okay, that's exactly the same sum of the moments as we had from the last problem because we have the same free body diagram. Now we have a different kinetic diagram, so we need to figure out the right-hand side of the problem here. We're going to get that from our kinetic diagram. From our kinetic diagram, we're going to treat each one of those pseudo forces as if they were a force. So for a second, just forget that they're pseudo forces and call them forces. I'm going to go ahead and do it specifically here. I'm going to say, let's call this force in the x direction. Let's call this force in the y direction. Now we know those aren't actual forces. Those are the cause of all the forces that are acting on it and the accelerations. So if we look at those as just forces and we use the kinetic diagram, we know that it's going to be the force in the x direction times this vertical distance here which we already figured out was 2 meters times the sine of 60. So I'm going to write that. Force, pseudo force in the x direction, 2 meters sine 60. And the way that I have it drawn is actually incorrect. The reason that I'm saying it's incorrect is because we are still sitting on the ground, and if we're sitting on the ground and we look at point A is not going to be going to the right. It's going to be going to the left. It's just not going to be going as quickly as the truck. So I'm going to go ahead and change my arrow. Now, I wouldn't need to. I could keep my arrow in the positive x direction. I'd end up just with a negative sign, and that's perfectly fine. And actually, why don't I just show that? So I'm going to keep it the way it is. But by looking at the truck, when the truck starts moving, in relationship to the truck, B is going to be rotating. But in relationship to the ground, B is going to be moving with the truck like that. So it's actually going to start off going in the x direction. I'm going to leave it in the positive x, and we'll just find the negative signs as we go. Okay, so force of x times 2 meters times sine of 60. If I put my thumb at A and I point it towards this pseudo force Fx, it's going to be pushing my fingers backwards, which is going to be negative. So I'm going to make sure I have my negative sign there. Okay, and then I'm going to do the same thing for the pseudo force in the y direction, which is pointing straight up. I put my thumb on A, I point my fingers towards it. It would also tend to rotate my fingers backwards, so that means that that's also negative. So it's going to be negative, that pseudo force in the y direction. And the distance that we need is going to be the same distance we use for the weight, which is this distance here, which is 2 meters times the cosine of 60 degrees. Okay, now finally we cannot forget about that IG alpha that we put in there. And you notice that I have it currently pointing in the negative direction. I want to stay consistent. And so what I'm going to do is I'm actually going to switch that one so that I have a consistency. And when I say stay consistent, I'm just saying that you should either choose to put everything in the positive direction and then solve for the negative signs, or you should choose to put it in the direction it's actually going. Either way, it doesn't matter as long as you stay true to your diagrams. So whichever way the arrow is pointing, you write as positive. If you solve for it and get a negative, you know the direction's the opposite of the way your arrow is pointing. I'm just going to go ahead for consistency's sake and erase this and put it in what would be the positive k direction, even though we know that the ladder will actually be rotating in the opposite direction. That's not a problem. We'll just end up getting a negative alpha. Okay, so if IG alpha going in that direction, you can see that that would give me a positive k. So I'm going to go ahead and write it as positive IG alpha. There's an equal sign in here, so that's our full equation. We have everything on the left-hand side, we have everything on the right-hand side. Now I'm just going to substitute back in that Fx and that Fy with the pseudo forces that they were. Looks like I lost my mass here, put that back in. And write out the full equation. Let's see if I'll have enough room for it. Get 20 kilograms, 9.81 meters per second squared, 2 meters cosine 60 degrees is equal to negative Fx is going to be the mass, which we know. I'm going to write it symbolically, and then I'll plug in the numbers. Mass times the acceleration of the center of mass of the ladder in the x direction. That's our pseudo force in the x direction. We're multiplying that by 2 meters times the sine of 60 degrees. And then we've got mass times our pseudo force in the y direction times 2 meters cosine 60 degrees. And finally, our IG alpha. Okay, so let's look at our knowns and our unknowns. You notice that everything on the left-hand side is known, so we're good to go there. On the right-hand side, there are quite a few things that we don't know. IG, now that's just the moment of inertia of the center of mass of the ladder. The problem told us it was a slender rod, so even though we haven't calculated it yet, we're pretty confident that we'll be able to calculate that. So we're going to call that a known. I'm only going to underline the unknowns. The mass is obviously a known. It's given in the problem. But we have 2 or 3 unknowns here. We have this acceleration, center of mass in the x, acceleration, center of mass in the y, and then alpha. So what we need to figure out is how those are related so that we can solve this problem. Because you notice this is a scalar problem. We can't solve for 3 unknowns. We need some more equations in order to solve for 3 unknowns. We need 2 more equations. And in order to do that, what we need to go back to is our relative acceleration equation. Now, our relative acceleration equation we've used many times. That says the acceleration of one point, let's say g, and this is a vector equation. Acceleration of one point would be equal to the acceleration of a plus alpha crossed with the position of, that should be g, position of g with respect to a. Remember the pseudo cancellation there. Minus omega squared position of g with respect to a. You can notice here I'm using the planar shortcut because we do have planar motion here. The planar shortcut is shortening down omega cross r to negative omega squared r. Okay, so that'll give us our relationship between the acceleration of g, the acceleration of y, the acceleration of the x, and of course our alpha. And this is the kinematic portion of this problem. To do this, well, we know that our acceleration in the a direction, we know that it's going to be, the acceleration of point A, we know that that's going with the truck. I'm going to go back up here to our given, and I'm going to say the acceleration of A equals the acceleration of the truck. And I'm going to go ahead and make those into vectors and say, well, that is going to be negative 6 meters per second squared in the I direction. Now we have it as a vector, and we can plug it into this equation. Our alpha, we know, is going to be in the k direction, so I'm going to say that our alpha as a vector is equal to the magnitude of alpha in the k direction. That way we have alpha in there as a scalar, and we can keep k for our cross products. And then we need to figure out the position of g with respect to a. Now we've already done that a few times. If you look at our equation up here, I could draw the position vector. The position of g with respect to a would look like this. We know that it's 2 meters long, and we know that there's an angle of 60 degrees. So it's pretty easy to get our coordinates of that. The position of g with respect to a as a vector would just simply be negative 2 meters cosine 60 degrees I plus 2 meters sine 60 degrees j. Then we have to ask ourselves, what's our omega squared? Well, our omega squared, this is where you have to read the question very carefully. So it asks for the initial acceleration. So the initial acceleration, what's our omega going to be? Well, initially, our velocity of the truck is equal to 0. So if our velocity of the truck is equal to 0, well, the ladder's not doing anything. So our initial omega is also going to be equal to 0. So this omega is actually going to cancel out because initially the ladder is not rotating. And you can see that we now have everything we need to plug into our equation. So we can write it as AGXI plus AGYJ is equal to my alpha of A, which is negative 6 meters per second squared I, plus alpha K crossed with my position of G with respect to A, which is negative 2m cosine of 60 degrees I, plus 2m sine of 60 degrees J. I want to point out here that we haven't labeled G, so I'm going to go ahead and label it. And also be very clear that point G is not the same thing as point B. Point B is up above point G. This is B here, and G would be right in the middle, somewhere down here. So we're using that G because we're using our kinetic moments. And our kinetic moments are always going to be about that center of mass, which is 2 meters from A, not 2.5 meters like B is. Okay, so we have this equation here, and we can solve for AGX and AGY just by using the I and J directions. So I'm going to start off by using the I direction. I'm going to take the direction out there, and then I can write everything in scalar form. I get AGX is equal to, everything on the right-hand side with an I. We get negative 6 meters per second squared. Now I need to figure out from my cross product what I'm going to get an I out of. I'm going to go ahead and do my shortcut, ijk. If we're crossing a k with an I, we're going to get j, so that's not going to be part of this equation. But when we cross the k with the j, we're going to get negative I, because it goes opposite direction of the arrow. So when we cross this k with the 2 meters times the sine of 60 degrees, that's a degree sign, not an equal sign, we're going to get an I, and we have to throw in a negative sign because we're going opposite of the arrow, so it would be negative 2 meters times alpha times the sine of 60 degrees. Okay, you notice that we have AGX in terms of alpha. That will get rid of one of our variables in the equation that we already wrote down up here, this longer equation. It'll get rid of one of our unknowns, AGX, and replace it with an alpha, which is what we're searching for, so that's great. Now we're going to do the exact same thing at the very bottom here. Hopefully I'll have enough room. We're going to do it in the y direction, and we can see AGY is going to be equal to what's in the j direction. Well, we just have to look at our cross product. When we cross k with I, we're going to get positive j, but there's already a negative sign there, so that negative sign carries through. It's going to be negative 2 meters times our alpha times the cosine of 60 degrees. Look at that. We now have AGX and AGY both in terms of alpha. And since we have both of those in terms of alpha, we can plug those into the long equation we have above, and we only have one variable that we can solve for. That's the last step we have to do here. So I'm going to go ahead and do that. Okay, and to solve for those, I'm just going to take the 3 equations we have and copy them onto a new slide. Okay, here are the 3 equations we have. The first one was the equation that we got from the sum of the moments about point A is equal to the sum of the kinetic moments. The second and third one are from the I and j directions of solving for the acceleration at point G relative to A. Now that we have these 3 equations, we can combine those. And if we look at our unknowns, we notice that in each of them we just have the unknown alpha, so we're going to have one unknown left. And we just have to make sure we have all of the other variables here, and the one that we're going to need specifically is the moment of inertia about the center of mass of that slender rod. So what you have to do is look in the back cover of your textbook, looking at a slender rod about the center of mass G. We're looking for, I'm going to use the IXX because that's the axis passing through the same as what we're looking at here. And that is going to be IG equals 1/12 ml squared. And we know that the length in this case, we look back at our picture, the length is the 1.5 meter plus the 2.5 meters, which would be 4 meters. So our L is 4 meters. And the mass was given as 20 kilograms. So we can plug that in and we have our full equation. I'm going to combine a few things here because it's going to be, well actually I'll write it out. I'll write the full thing out and then we'll start combining things and solving it. So first thing we've got 20 kilogram, 9.81 meters per second squared, 2 meters cosine 60 is equal to 20 kilograms. Forgot my negative sign, is my negative sign. And then we put the acceleration in the x direction, which would be negative 6 meters per second squared minus 2 meters times alpha times the sine of 60. Then we have to multiply all that times 2 meters times the sine of 60 degrees again. Okay, I'm going to go down to the next line just so that I have room. I'm just copying down from up here. The next term there we would have negative 20 kilograms. Then I have to plug in the acceleration in the y direction. And it looks like I wrote these both as x. I made a mistake up here. The acceleration in the x direction is correct, the first one, but the second one should have been the acceleration in the y direction. Multiply all this by acceleration in the y direction, which is 2 meters times alpha times the cosine of 60 degrees. Multiply that whole thing again by the cosine. 2 meters times the cosine of 60 degrees. And then we have to add that to our moment of inertia about the center of mass, which is 1/12 times 20 kilograms times the length, which is 4 meters squared, and multiply that by alpha. So each one of our terms has an alpha in it, except for the one on the left-hand side, the equal sign. Now it's just a calculator exercise to solve for alpha. Okay, and calculating all that out, we have on the left-hand side, the equal side is 196.2, and you can see we have the kilogram meters per second squared times meters. That's going to be Newton meters is equal to. Then we get a constant of, well, not a constant, but a term without alpha in it, 207.85 Newton meters. And then that's multiplied by the -6 meters per second there. And then we have to get the term with the sine of 60 in it, and that's going to be 60 plus 60 alpha. The 60 comes from this term multiplied by this term multiplied by all that. That's where we get 60. Then we get a 20 from the next term, which is this term right here. That one turns out to be 20. And then to that we add 20.6 repeating alpha. Add those together and we get 106.6 repeating is equal to negative 11.65. Oh, I forgot my alpha. 106.6 repeating times alpha is equal to negative 11.65. Go ahead and solve for alpha. Alpha is equal to negative 0.109 radians per second squared. Good thing we got negative. If we hadn't got negative, something was wrong, remember, because at the beginning, when I drew my kinetic diagram, I chose to have alpha in the positive direction, even though we know by looking at it that the ladder would actually rotate in the clockwise direction. I drew my alpha in the counterclockwise direction, which would be positive k. Now the answer we're going to write out as a positive because what the question asks, if the truck accelerates at a constant rate, determine the initial angular acceleration, the 20 kilogram ladder. So initial angular acceleration would be alpha equals 0.109 radians per second squared. Which way is it accelerating? It's accelerating in the clockwise direction, or you could write clockwise. And there's our final answer. So with this one we used our kinetics, and we also used kinematics. You can see that we combined those equations at the end. And you notice that I didn't use some of the forces in the x and y direction. You absolutely could have, but it wouldn't have given you all of that much information. We could solve for the reaction forces at A, but we didn't need that to solve our problem. Hopefully you can see that the kinetic diagram is a very powerful tool to combine the parallel axis theorem with the equations of motion in a visual manner. And that's what it's used for. Hopefully this has been helpful to you. Please let me know if there are any questions, and I encourage you to practice these methods on the homework problems. Thanks.